Sometimes when we're doing stoichiometry problems, if they involve gases, we may need to incorporate the ideal gas law. An example would be practice 10.19 in your textbook. It says carbon disulfide is an extremely flammable liquid. It can be ignited by any small spark or even by a very hot surface such as a steam pipe. The combustion reaction is, and then it gives us, like all stoichiometry problems, we need to know the balanced chemical equation because we're going to use the coefficients as ratios. So here's the balanced chemical equation that was given. It says when 11 grams of CS2 is burned and excess oxygen, what total volume of CO2 and SO2 is formed at a temperature of 28 degrees Celsius, which we know if we add 273 is 301 Kelvin, and 883 torr, 883 torr, which if we convert that, we get 1.16 atmospheres. Okay, so thinking about it, they ask us for both CO2 and SO2. So in this particular stoichiometry problem, I'm given grams. So I know that if I know the grams of CS2, I can convert that to moles using the molar mass of CS2, which I already calculated. And then if I want to know the amount of carbon dioxide, I can multiply by the ratio from the balanced chemical equation, which is 1 to 1, and I would get that it would produce 0.144 moles of carbon dioxide. And then if I could do the same thing, and I guess I could have gotten an intermediate answer and that would save me a step here. But if I convert, it's moles, the grams of CS2 to moles of CS2, and then to find the SO2, if you're looking at the chemical equation, the coefficient for the S here is 2. So I have a ratio of 2 to 1. And so then I get 0.289 moles of SO2. Okay, so once I know the number of moles, this is where the ideal gas law comes in. Up to this point, it's just been like any other stoichiometry problem. But both CO2 and SO2 are gases, and so they want us to calculate the total volume of CS2 and SO2. So what I can do, and I'm going to move to the next page, the ideal gas law says that PV equals nRT. I can calculate the volume by taking the number of moles times R times T and dividing it by the pressure to get the volume. So first let's do for CO2. The number of moles I calculated was 0 on the previous page, 0.44 times R and the temperature, which I calculated on the other page, 301, and then the pressure that I had calculated on the other page was 1.16. And if I calculate this, I get the volume of the CO2 to equal 3.07 liters. Now, I could also calculate the volume of the SO2 in a similar way. But I also know that I can use the ratio from the balanced chemical equation. And so if we look back at the equation, I see that it is a 1 to 2 ratio. So I can say it takes 2 liters of SO2 for 1 liter of CO2. So then this equals 6.14 liters. I used Avogadro's law here. We know that volume is proportional to the number of moles when they're at the same temperature. So instead of using the ideal gas law the second time, which I could have and would have gotten the same answer, I just used the ratio. Now, once the total volume, so to get the total volume, I would add the 3.07 liters from the carbon dioxide to the 6.14 liters of the CO2, and so the total volume is 9.22 liters.